When the space shuttle was designed, the goal was to create a reusable orbiter that could be used again and again to lower the cost of spaceflight and to avoid having disposable spacecraft. And so the wings are another indicator of that, because the spacecraft had wings and could glide safely to a landing on Earth. It could be serviced on the ground and could fly again. And in fact, the 5 space shuttle orbiters flew a combined total of 135 missions over a 30-year period. That, too, had never been done before. But the other distinctive feature of the space shuttle is not evident from a distance, but as you walk closer and closer to it, you see that its surface coverings are quite varied. There's a lot of texture there. And as you approach, you notice that the white parts of the shuttle are actually a patchwork quilt of thermal blankets, actually fabric that conforms to the shape of the vehicle. And the black part of the shuttle actually looks like a wall of tiles, squares and other shapes of that look like tiles cover the entire lower surface of the shuttle and other parts along the edges, and part of the nose and around the windows. And that is very peculiar. No other spacecraft beforehand had that kind of a multi-textured, multi-form exterior. And it's really a shell that encompasses the entire vehicle underneath. Finding the right heat shield for the space shuttle was one of the most difficult challenges, but now we can continue using that technology to keep bringing our vehicles and our astronauts safely home.
On February 1st, 2003, the Space Shuttle Columbia was preparing to come home after a successful 2-week science mission studying the effects of microgravity. The commander of the mission, Rick Husband, prepared the shuttle for entry by performing a deorbit burn, with the thrust acting against the direction of flight to lower the orbital speed of the shuttle and begin the descent trajectory. The shuttle then maneuvered into a high angle of attack orientation of about 40 degrees to allow atmospheric drag to have a maximum effect and decelerate the shuttle for its return home. The initial speed was over Mach 25 and was bled off by the action of aerodynamic drag. And during the entry trajectory, both the deceleration and aerodynamic heating build up to perilous levels. Sadly, the 7 astronauts on board didn't make it all the way home. The Space Shuttle Columbia broke apart in mid-flight on their way to an intended touchdown at Cape Canaveral, Florida. Debris from the breakup rained down a large swath of Texas and Louisiana as the shuttle disintegrated in flight. It turns out that intense aerodynamic heating led to the untimely demise of the Shuttle Columbia and her crew. The problem actually started at liftoff, 2 weeks earlier, when a large piece of foam broke off the external tank and collided with the leading edge of the Columbia's left wing. The collision actually punched a large hole in the thermally protected leading edge, perhaps 1 or 2 feet in diameter. This gaping hole wasn't a problem until it was time for Columbia to return home. Then, when the shuttle's thermal materials were supposed to protect the Columbia from the intense heat of atmospheric entry, there was a huge, vulnerable hole instead. Hot gases building up around the vehicle during entry actually entered the wing and melted the shuttle's structure from the inside out. The melting structure could no longer carry the aerodynamic loads on the vehicle, and the wing broke off. Subsequently, the entire shuttle broke up into pieces, leading to an absolute disaster. This tragic accident reveals how perilous atmospheric entry can be. For the Columbia astronauts, getting home was the hardest part of their journey. So what are the scientific reasons why this portion of spaceflight is so fraught with danger? The peril is explained by the science of energy dissipation and aerodynamic heating. A spacecraft returning to Earth will have incredibly high velocity. Just returning from Earth orbit entails a velocity of over 7 kilometers per second. And for returns from interplanetary visits, the velocity has to be at least as high as the Earth escape trajectory of around 11 kilometers per second. This leads to incredibly high kinetic energy. And as the spacecraft returns to Earth, decreasing its potential energy along the way, its kinetic energy must go up even more. So from conservation of energy, the spacecraft will actually be accelerating as it approaches Earth. Somehow we have to take this high-speed, accelerating spacecraft and safely bring it to a complete rest on Earth's surface. In other words, we have to somehow get rid of all of that excessive kinetic energy. One option is to fire rocket thrusters against the direction of flight in order to slow the spacecraft down. This is an effective maneuver, but it would take a substantial amount of extra fuel. Spacecraft in Earth orbit will start the process of atmospheric entry with a short deorbit burn, but carrying a lot of extra fuel for this would merely crowd out mass for people and equipment to carry out the mission. The other option, really our main option, is to decelerate the spacecraft by the force of aerodynamic drag acting against the vehicle. In fact, this is an inevitable consequence of entering the Earth's atmosphere. The spacecraft must encounter aerodynamic drag from interaction with the air molecules, and that drag will slow the spacecraft down. And as the spacecraft slows down and descends at the same time, its energy is decreasing dramatically. Based on conservation of energy, we know that this dissipated energy can't just disappear. It has to go somewhere. All of that high kinetic energy and potential energy is ultimately dissipated as heat. The amount of energy that we're talking about is incredibly high, and that leads to extremely high temperatures. For perspective, let's consider the energy that a shuttle has immediately after a deorbit burn to start atmospheric entry. At this point, the shuttle at its maximum landing mass of 100,000 kilograms and at a speed of about 7.7 kilometers per second will have kinetic energy of almost 3 times 10 to the 12th power joules. And if the shuttle was in orbit with the International Space Station at an altitude of 400 kilometers or 249 miles up, then the potential energy that is lost during entry is about 3.7 times 10 to the 11th joules. Adding those up, the shuttle dissipates 3.3 million megajoules within just about half an hour. If heat could be converted into electricity, that would be an average power of 1.8 gigawatts. Now, pushing this into the realm of fantasy or science fiction, if we could somehow harness that energy and channel it into a flux capacitor, it's more than enough to provide the 1.21 gigawatts needed to power Doc Brown's time machine and Back to the Future. So for a spacecraft to initiate an atmospheric entry maneuver from Earth orbit, it initially will perform a retrograde burn to bleed off enough of its speed to enter the atmosphere. In that lower orbit, even in the thinnest outer reaches of the atmosphere, aerodynamic drag will start to act on the vehicle to slow it down. Moreover, it's quite possible to enter and exit the atmosphere more than once to dissipate even more energy. Apollo missions had an unused capability called skip guidance that allowed for the possibility of dipping briefly in and out of the atmosphere before continuing its descent at a lower rate. 3 U.S. missions to Mars have used a far more prolonged version of multiple entries called aerobraking. Because the Martian atmosphere is so thin, hundreds of passes in and out of the atmosphere are made over a period on the order of 3 or 4 months. Now that raises a question. Exactly how thick is Earth's atmosphere? Or put another way, where does space begin or end? Well, it really depends on the density of air and how that varies with altitude. As we saw in our second lecture, the density decreases with altitude exponentially, meaning that most of the air molecules are clustered near the Earth's surface. There is an exponential decay of air density as we continue out to the outer reaches of the atmosphere. Even this vanishingly small amount of air can have an impact on the spacecraft if we're not careful. For example, the International Space Station still encounters the effect of air, however small, at a height of about 400 kilometers or 249 miles. In fact, the orbit of the space station was initially at 350 kilometers, But over time, the mission controllers found that the aerodynamic drag was so significant that in 2011, they used about 10,000 pounds of propellant to boost the space station to 400 kilometers, where they expected to cut in half the annual fuel of 19,000 pounds per year previously needed to maintain the station's orbit. Smaller spacecraft, such as the Space Shuttle or typical satellites, experienced less of an effect from aerodynamic drag, because the area of these vehicles is fairly small. However, the space station is relatively huge. It measures on the size of the American football field, with the end zones included. Such a large surface area provides a much bigger target to interact with air molecules, leading to much greater drag. To overcome the drag, which would tend to destabilize the orbit and ultimately bring the space station down, mission controllers had to perform a number of orbital burns to provide the delta V needed to maintain the desired orbit. So they were consuming around 19,000 pounds of fuel every year just to keep the station on track. But this fuel had to be shipped up to the space station on a regular basis, which of course is very expensive. With launch costs ranging between $1,000 and $10,000 per pound to low Earth orbit, this fuel cost translates to between $19 million and $190 million per year just to overcome aerodynamic drag. Clearly, that was strong motivation for increasing the orbit's altitude. But there are always trade-offs. A higher altitude orbit means additional per-launch cost for resupply ships to reach the more distant space station. And if the orbit were placed too high, astronauts would lose protection from the solar radiation provided by particles in the inner Van Allen belt, whose altitude starts at a variable altitude of 200 to 1,000 kilometers. Okay, so the effects of the atmosphere continue out into space along a gradient with vanishing impact. This makes it harder to define space as beginning at any single boundary or discrete edge of the atmosphere. But that hasn't stopped us from doing so. According to the U.S. Air Force, space begins at an altitude of 80 kilometers, or 50 miles. Above this height, pilots get their astronaut wings. Another common definition of space, used internationally, is the metric-based Kármán line, which is at 100 kilometers, which is 62 miles or 330,000 feet, 10 times the typical cruising altitude of commercial airliners. At this altitude, Theodor von Kármán calculated that an aircraft would have to travel faster than the orbital speed of 7.9 kilometers per second in order to generate enough lift to sustain flight in the rarefied air at the outer reaches of the atmosphere. Or, in other words, at an altitude of 100 kilometers and above, an airplane has too little air available to generate the lift it needs to stay aloft at that altitude. Successful flight above that altitude means you are in a spacecraft and maintaining flight relatively free of aerodynamics. Although there is too little air beyond this point to lift an airplane, the ability of air to create drag continues to higher altitudes. A spacecraft will stay in orbit, at least briefly, at a height of 160 kilometers, or 99 miles. At altitudes lower than this, the outer reaches of the atmosphere will exert enough drag force on an orbiting body to cause it to slow down and eventually return to Earth if no additional thrust is provided to overcome that drag. So 160 kilometers can be considered a lower boundary for a drag-based edge of space, even though smaller amounts of drag are found even hundreds of kilometers above this altitude. Most of our satellites, and all of human orbital spaceflight, have been in these initial layers of space, where tiny amounts of drag are still present. This is low Earth orbit, rising to a maximum distance of roughly 2,000 kilometers, which is in an upper bound for protected by the inner Van Allen belt. Interestingly, most of these distances above the Earth are very small compared to the radius of the Earth. The space station's orbital altitude of 400 kilometers is only about 6% of the Earth's radius. That is a path that barely scrapes the surface. If we were to scale the Earth down to the size of a tennis ball, the orbit of the space station would be right about the height of the fuzz on the ball. So the atmosphere can have a mild effect on the spacecraft that want to stay in orbit, but there is a huge effect on spacecraft that are returning home. There are three main methods to enter the atmosphere from space. First is the ballistic entry, where pretty much only atmospheric drag is acting on the vehicle. Any lift produced is very small, giving a lift-drag ratio of less than 1. Because lift is so small, pilots have little control of the spacecraft's trajectory. Instead, the spacecraft simply falls back to Earth and lands wherever the trajectory takes it. All of NASA's early missions, including Mercury, Gemini, and Apollo, were ballistic entries, and the landing zones were always over water due to the lack of precision control of the landing site. Next is the skip entry, where the vehicle has a lift-to-drag ratio of between 1 and 4. Using a modest amount of lift, the astronaut can manipulate the trajectory of the spacecraft to dip into the atmosphere a little bit, exploit the lift acting on the spacecraft, and pull back out with a reduced velocity. Then the process could be repeated a number of times, if desired, to gradually reduce the spacecraft's velocity. This type of entry is similar to skipping a stone across water. The velocity of the vehicle decays with each skip, just like the speed of the rock drops with each skip until it finally plunges into the water. The difference is that the upper layer of the atmosphere is curved, so a skip entry means riding along that curve. The challenge of a skip entry is that the atmospheric heating builds up with each skip, potentially leading to higher overall heat loading on the spacecraft. The third entry maneuver is a glide. For this type of entry, the spacecraft must generate enough lift to substantially alter the trajectory of the vehicle. With lift-to-drag ratios of 4 and higher, this trajectory allows precise control of the touchdown location and a much longer distance between the beginning of entry and touchdown. For example, a typical shuttle flight with a lift-to-drag ratio of 4.5 would first encounter the atmosphere on entry while still over 5,000 miles away from Kennedy Space Center. The differences between these profiles can be striking. For example, the ballistic entry of Apollo and Gemini spacecraft were much faster than the glide entry by the shuttle, which took about 3 times as long to descend from the outer edge of the atmosphere. This results in different profiles for deceleration and heating. The ballistic trajectory of NASA's early spacecraft had much higher deceleration, about 6.5 Gs, and higher peak heating rates. The shuttle, on the other hand, had much lower peak deceleration, only about 2 Gs, lower peak heating rates, but with a longer entry, also higher cumulative heat load. Now, there are 2 main constraints on the entry of a spacecraft into the Earth's atmosphere for a safe landing. One is the maximum amount of deceleration encountered by the spacecraft. The second is how much it heats up. If the trajectory of a spacecraft through Earth's atmosphere is too steep, then the G loading will be too high for the astronauts, and the intense heating rate could lead to the spacecraft burning up. So a trajectory that is too steep would either crush or burn the astronauts, or both. However, if the spacecraft enters with too shallow of an angle, an overshoot beyond the desired trajectory results, with the risk of skipping off the atmosphere. With a shallow angle of entry, if the velocity of the spacecraft is high enough, greater than the escape velocity, the spacecraft could stay on an outward trajectory that would send the spacecraft careening off into space, lost forever. These 2 constraints, from gravity and from temperature, define an incredibly narrow entry corridor that the spacecraft must achieve. It's like threading the eye of a needle to get it just right. The risks of this narrow entry corridor were clear with the drama of Apollo 13.
We may have had an instrumentation problem, flight.
Roger. And we had a pretty large bang associated with the caution and warning there.
The astronauts were on a spacecraft with extremely limited fuel, since their primary means of maneuvering had been disabled by the explosion of an oxygen tank in the service module of their spacecraft, while on the outbound leg of their journey to the moon. After rounding the moon on the free return trajectory, they were on a course back towards Earth. The problem, though, was that the trajectory they were on would not line them up with the correct entry corridor. And doing maneuvering burns with their crippled spacecraft was extremely challenging. They were using the lunar module for all of their maneuvering, but this was not the original design intent of the Aquarius module. But since it was all that they had, the mission controllers went through extensive planning, calibration, and alignment to get the burn just right. So after the astronauts rounded the moon on the free return trajectory, they performed a carefully calculated burn of exactly 4 minutes and 24 seconds in order to get established back on course. This burn then lined them up perfectly for the optimal entry corridor, defined by a descent angle of 6.5 degrees. To get a sense of how precise this course had to be, let's consider how wide the entry corridor was. If the Apollo 13 astronauts came in at an angle below 5.3 degrees, just 1.2 degrees below optimal, they would overshoot the desired trajectory and skip off the atmosphere. and their velocity was high enough that this skip would result in an escape trajectory, hurling them off into space, forever marooned in their crippled spacecraft with no hope of return. On the other hand, if their spacecraft came in at an angle steeper than 7.7 degrees, their descent would be too aggressive, leading to excessive G-loading and high aerothermal loading on the spacecraft. So if they came in too steep, they risked burning up and getting crushed on the last leg of their already perilous journey. This illustrates how very narrow the entry corridor is, just plus or minus 1.2 degrees to work with. And since their spacecraft was crippled with unknown dynamics, there was a huge risk that they wouldn't make it. For example, while they were coasting on the return leg from the moon, they began to gradually drift off course. Over time, it became clear that they were going to drift off the optimal trajectory, leading to the precipitous edge of the entry corridor. So the mission controllers had them do 2 more mid-course correcting burns while en route, despite the scarce fuel supply on board and the substantial risks involved every time they fired up the engine on the lunar module. Despite these course corrections, Apollo 13's capsule was still coming in at a slightly low angle. Compounding the risk of being off the required trajectory was the concern that the space capsule's heat shield had been damaged in the explosion on the service module. A damaged heat shield would provide less protection to the capsule during the intense heating of atmospheric entry, possibly leading to incineration of the capsule. And to heighten the drama of the entry process, the astronauts would be out of radio contact with mission control during a blackout period in the heat of entry. This radio blackout results from ionization of the air molecules surrounding the capsule, which inhibits radio propagation. During that window of time, mission control would have no idea how the astronauts were doing. No voice communications and no telemetry data were available. If the spacecraft encountered difficulty, they wouldn't know and wouldn't be able to provide any help. So mission control expected to reestablish radio contact after a 4.5-minute blackout period. However, an additional 87 seconds went by before contact was reestablished due to a shallower than planned entry angle through the blackout zone. At this point, the worst was over. The astronauts on board the crippled spacecraft had prevailed. The capsule continued its descent and parachuted into the South Pacific Ocean for a successful return. Let's now take a close look at the critical issues that the Apollo 13 astronauts faced as they hit that entry corridor just right: deceleration and aerodynamic heating. For a ballistic entry trajectory, we can assume that aerodynamic drag is the dominant force acting on the spacecraft. Other forces, such as lift, can be neglected. Even the effect of gravity can be neglected compared to the high level of drag involved. So, when applying Newton's second law, F equals ma, we can solve for the deceleration and see that it's equal to the drag divided by the mass of the vehicle. Taking our expression for drag that we've seen many times in this course, we can explore the effects of density and instantaneous velocity on the deceleration, or G-loading, that the spacecraft experiences. So with drag substituted into Newton's second law, we see that deceleration is equal to the product of density, the square of velocity, a reference area, and a drag coefficient, all divided by twice the vehicle mass. A plot of altitude versus velocity for the spacecraft's trajectory confirms that the spacecraft will start decelerating when it encounters the outer regions of the atmosphere, descending and decelerating until lower altitudes, at which the rate of deceleration trails off. Instead of looking at velocity, another way of looking at the trajectory is to consider the variation of deceleration with altitude. This is a helpful view, since the maximum deceleration is the maximum G-loading that the spacecraft encounters. As the deceleration starts building, slowly, the spacecraft encounters the outer regions of the atmosphere. As the spacecraft descends, atmospheric density increases, the drag builds up, and the deceleration increases dramatically. At a specific altitude, there will be a peak deceleration with maximum G-loading. Beyond this point, the decrease in velocity overcomes the increase in density, and the overall drag starts to decrease. Since the deceleration is directly related to the applied force, the deceleration decreases as the drag goes down. Now, there's a grouping of terms that we'll recognize now, which will simplify our deceleration equation somewhat. We can define a ballistic coefficient, which describes the effect of drag on the spacecraft and strongly influences its trajectory. The ballistic coefficient is the vehicle's mass divided by the product of drag coefficient and reference area, and its value is fixed for a given spacecraft. Spacecraft designers configure the size, mass, and shape of the spacecraft in order to get the desired ballistic coefficient. And this coefficient has a huge impact on the spacecraft's entry trajectory. A low value of ballistic coefficient indicates a lightweight, large area, or high drag vehicle. This type of spacecraft will begin to decelerate at higher altitude. Higher values of ballistic coefficients are for heavier, smaller, or lower drag spacecraft. These vehicles will descend deeper in the atmosphere before the drag starts to take hold and decelerate the vehicle. So the ballistic coefficient has a significant impact on the altitude where peak deceleration takes place. Now, from Newton's second law, the maximum deceleration is proportional to the product of the square of the entry velocity and the sine of the entry trajectory angle. This reveals the critical dependence of max deceleration on the entry velocity and the entry angle. High energy trajectories, such as on a mission to the moon or another planet, will have high return speeds in excess of 11 kilometers per second when approaching Earth. So these higher velocity missions will inherently have far higher maximum G loading. But there's not much more that can be done about velocity. However, we can control the entry trajectory angle. A shallower angle will give lower values of deceleration, keeping things manageable. This is why the Apollo missions had such a small entry angle of 6.5 degrees. Any steeper and max deceleration would have been a problem. So entry angle is the key parameter that we can use to control the magnitude of peak deceleration. Also note that the ballistic coefficient doesn't appear in the equation for max deceleration. So the ballistic coefficient will affect the altitude at which max deceleration occurs. It has no bearing on the peak value of deceleration that is encountered. We're now going to turn our attention to the other critical physical parameter that limits aerodynamic and atmospheric entry, aerodynamic heating. Now, the dissipation of a spacecraft's huge kinetic energy must take on the form of aerodynamic heating. By conservation of energy, there is nowhere else for that energy to go. In fact, as the spacecraft streaks through the atmosphere at hypersonic speeds, a very strong shock wave forms ahead of the vehicle. Between the shock wave and the spacecraft, the temperature of the air is astoundingly high. In fact, on the high velocity entry of Apollo, the temperature right next to the capsule reached as high as 11,000 degrees Kelvin. That's over 19,000 degrees Fahrenheit. This temperature is so high that it's about twice the temperature of the sun's surface. The rate of heating of the air has a functional form similar to the drag equation, except it depends on the cube of velocity instead of velocity squared. We can express the heating rate as being equal to the product of 1/2 density, velocity cubed, reference area, and a non-dimensional coefficient called the Stanton number. From this, we see that velocity, which is cubed, has a dramatic influence on the heating rate throughout entry. If we examine the heating rate at all altitudes, we see that heating rate increases as the density goes up, reaches a peak, and then decreases again as the velocity goes down. Now, a safe return of our spacecraft depends not only on keeping the peak heating rate under control, but also the total heat load accumulated by the spacecraft during the entire descent. The total heat load is equal to the product of 1/2 times the ratio of a skin friction coefficient to the drag coefficient times the kinetic energy of the vehicle at entry. Again, we can't do too much about the velocity, which is kinetic energy of the vehicle at entry, since that depends on the type of orbital trajectory. Hyperbolic trajectories from other planets will have the highest kinetic energy, which must ultimately be dissipated as heat. However, we can control the ratio of skin friction to drag coefficients by tailoring the shape of the spacecraft, which controls the ballistic coefficient for the vehicle. A blunt, rounded shape is best for maximizing the drag coefficient and forming a detached bow shock off the front of the vehicle. This leads to a reduction in the aerodynamic heating, compared to a vehicle with a sharp, pointy nose. The need to reduce the aerodynamic heating is why you'll never see a space capsule or space shuttle with a sharp leading edge. Even ballistic missiles will have rounded leading edges. For successful entry, we'd like for all of the aerodynamic heating to go into the air rather than into the spacecraft. The way to accomplish this is through careful thermal protection systems. Two main strategies have traditionally been discussed for protecting a spacecraft from this intense heat: thermal ablation and radiative cooling. The first strategy is to use an ablative coating called a heat shield. This involves heat dissipation by vaporization of the material used on the shield. Because phase changes of a material require substantial energy and yet don't result in a temperature change, this is a very effective way of controlling the temperature on the capsule surface. As the material ablates or vaporizes, it carries the heat away from the capsule instead of allowing the heat to build up on the surface. These ablative coatings were used on all of NASA's early missions where a ballistic entry was employed. Mercury, Gemini, and Apollo all benefited from this strategy, almost all of which worked without a hitch. One tense moment, though, occurred on John Glenn's first orbital flight on Friendship 7 on February 20th, 1962. Once in orbit, Mission Control noticed that a sensor for the landing system was providing a strange reading. Through a series of troubleshooting steps, Mission Control became seriously concerned that the heat shield had somehow come loose.
I still have some of these particles that I cannot identify coming around the capsule occasionally, over.
Roger. How big are these particles? Over.
Very small. I would indicate they're of the order of a 1/16 of an inch or smaller. They drift by the window, and I can see them against the dark sky. Just at sunrise, there were literally thousands of them. They looked like just a myriad of stars, over.
To hedge against this possible problem, the controllers instructed Glenn to keep the retro rocket pack attached to the heat shield instead of jettisoning it before entry as he normally would. The idea was that the presence of the rocket pack would help keep a loose heat shield in place. As the Friendship 7 capsule hurtled through the atmosphere, heating up along the way, Glenn saw huge chunks of burning material flying by his window, and he feared that these were from his loose heat shield. Thankfully, Glenn made it all the way back to Earth in one piece. It turned out that the flaming chunks of material were from the unneeded rocket pack, disintegrating as he came in. So ablative coatings are a very effective strategy for thermal protection and are widely used to this day. More recent spacecraft examples include the Russian Soyuz re-entry capsule and SpaceX's Dragon capsule. After rapid deceleration and heating through the atmosphere, these capsules descend the last few thousand feet via parachute. Now, the second thermal protection scheme is to use radiative cooling. This was the predominant approach used on the space shuttle, which required a reusable design. While the ablative coatings were extremely effective, they were thought not very well suited for a reusable spacecraft due to the unavoidable need for complete refurbishment after each mission. There was also concern about possible aerodynamic and control effects when an ablative coating vaporizes away during re-entry. So innovative thermal tiles were developed for the space shuttle, the most important of which were the black tiles surrounding the bottom and nose of the shuttle orbiter. The main features of these tiles are high emissivity and a high melting point. High emissivity means that the tile will radiate heat away very efficiently. The cooling effect of these high emissivity tiles is so quick that a tile removed from the hot oven or heated with a blowtorch can be touched with bare hands only a couple of seconds later. The combination of these tiles with an insulating thermal blanket underneath proved to be a very effective thermal management system for the space shuttle. Newer approaches to thermal protection have also been in development. For example, NASA has tested inflatable heat shields, where the inflatable would increase air braking while also increasing the surface area for spreading heat. So the key factors dictating the atmospheric entry trajectory of a spacecraft are atmospheric heating and the deceleration profile. Managing the thermal load and keeping deceleration levels low enough is what allows spacecraft to return home safely.